In this lesson, I want to look at the Pythagorean Theorem, perhaps in a new way that we haven't looked at it before. And so let's talk about right triangles and what the Pythagorean Theorem says. Now, I've drawn the picture of a right triangle, but notice I have not used the classical or traditional A, B, and C. And there's a reason why I haven't done that. Why should A, B, and C be universally representative of sides of a triangle? It just makes more sense just to say leg 1, leg 2, and hypotenuse. And that way, in mathematics, I can use A, B, and C for other things, and I don't have to always feel like A, B, and C have to be the sides of a right triangle. So I think it's more correct to use leg 1 and leg 2 and hypotenuse. Now, a right triangle has 2 legs and only 1 hypotenuse. And the hypotenuse, as you can see from the picture, is always going to be the longest side in a right triangle. That's just always true. So let's look at the Pythagorean Theorem in a way that perhaps you have not seen it before. Not using A, B, and C, but using what we have from the previous picture. Leg 1 square plus leg 2 square equals the square of the hypotenuse. That's the Pythagorean Theorem. And so in other words, if I take both legs, if I square both legs, and I add those numbers, then the result will be the square of the hypotenuse. So I've given some examples here, 3 examples of how to use these in the Pythagorean Theorem. So let's look at the first one, 3, 4, 5. I've put 5 in a box on purpose because 5 is the biggest number. Therefore, if I'm going to use these in the Pythagorean Theorem, 5 has to represent the hypotenuse. So 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16, and 5 squared is 25. And look what happens. I get an identity. 25 equals 25. And so therefore I know that 3, 4, and 5 are numbers that satisfy the Pythagorean Theorem. Let's look at 7, 24, and 25. Again, do you know why I put 25 in a box? Because it's the largest number there. And so it has to represent the hypotenuse. So 7 squared plus 24 squared is equal to 25 squared. 49 plus 576 equals 625, and I get the identity. An identity is an equation that's always true, no matter what. 625 equals 625. Now the numbers don't always have to be integers, nice whole numbers. So for example, these decimal numbers can work too. 1.5, 2, and 2.5. 1.5 squared plus 2 squared equals 2.5 squared. So 2.25 plus 4 equals 6.25, and I get the identity. 6.25 equals 6.25. Okay. Well, I don't know if you've heard of this term, but we're going to talk about Pythagorean triples. Now, like I said, the numbers that satisfy a Pythagorean equation don't have to be whole numbers. They don't have to be integers. However, there are a certain set of numbers that we call Pythagorean triples. And Pythagorean triples are always integers. They're always whole numbers that satisfy the Pythagorean Theorem. So in the examples I just gave you, only the first 2 qualify as Pythagorean triples, even though the third one works. 1.5 and 2.5 are not integers. Now, in my years as a math teacher, I've encountered that sometimes students have difficulty identifying the hypotenuse. And I've got a couple of ways maybe to help you today to identify the hypotenuse. So let me talk about the most traditional way first. The hypotenuse, by definition, simply by what it is the side opposite the right angle. So here's the right angle, 90 degrees. And so the side opposite is the hypotenuse. So this is the hypotenuse. But when people look at a picture, not everybody sees the same thing, unfortunately, when they look at the same picture. So perhaps this might be another way that would help. Take a right triangle, and if you're having difficulty identifying what the hypotenuse is, imagine making a rectangle out of it. Just imagine. The diagonal of that rectangle will be the hypotenuse. So maybe this way doesn't work for you. Then try and imagine making a rectangle out of the right triangle. And then the diagonal always goes from upper corner to lower corner. It could be going this way depending on how I draw the triangle, but this has to be the hypotenuse. Okay, well, let's talk about some very common misconceptions that students have when they work with the Pythagorean theorem. So I want to talk to you about a common mistake that I see many times, and my purpose of making this video is to help you to see it ahead of time so that you don't fall into the same mistake. And so let's say I have a pretend student named David, and I say, okay, David, here's a triangle. Find the missing side. So David looks and he says, well, it's a right triangle, so it has to obey the Pythagorean theorem. And so that means David sets up the following equation. He says 6 square roots of 3 squared plus 12 squared equals x squared, which is the unknown side. Well, 6 square roots of 3 squared is 36 times 3. I have a lot of students ask me sometimes, how on earth did you get that? You know what? I'm going to tell you at the end of this video. Just be patient and just accept that it is true for right now, okay? 36 times 3 plus 144 equals x squared. 36 times 3 is 108 plus 144 is x squared. 252 is x squared. So x is the square root of 252. And then I start to break down the 252. 2 times 126, 2 times 63, 9 times 7. And when it's all said and done, we get x equals 6 square roots of 7. But there's something tragically wrong here. Do you know what's tragically wrong? Maybe you do. But anyways, if this were the right answer, what else should be true? I mean, if this really is the right answer, then that means all three of these numbers should obey the Pythagorean theorem. So in other words, I hate that bell. So in other words, 6 square roots of 3 squared plus 6 square roots of 7 squared should be 12 squared. So 108 plus 252 is 144. Uh-oh, we see the problem. That's 360 is 144. No, didn't work. Ah, what went wrong? Where did David go wrong? Well, David rushed it, or he just didn't think. He didn't pay attention. Can you tell me what the hypotenuse is? It's 12. And so this is not the correct setup. What is the correct setup? It's this. And so 6 square roots of 3 squared is 108. X squared is x squared. And 12 squared is 144. Now I subtract 108 from both sides, and I get x squared is 36. So x is technically plus and minus 6, but again, this represents the side of a triangle, and a negative length just doesn't make any sense, so we just allow it to be 6, and that is a valid solution. So the missing side here is 6. So that's a very common mistake that I see many times. Students just rush through the problem, don't think. You got to slow down, okay? Don't be in a rush. All right, let me show you how easy it is to take something like 6 square roots of 3 squared and figure out the answer. So here's another example, 5 square roots of 3 squared. Well, what happens is the 5 is outside of the root. The 3 is inside of the root, and so that power of 2 is going to come down and influence both of those numbers. So this will become 5 squared times the square root of 3 squared. 5 times 5 is not 10, it's 25. And the square root of 3 squared is the square root of 9. But what number times itself is 9? 3. The square root of 9 is 3, and so 25 times 3 is 75. And so it turns out that if I take 5 and square it, and just drop the root, I end up with 75. For you algebra heads out there, I'm going to give you a nice handy dandy rule. A is any positive, well, who cares about positive? A is any real number, period. B is any positive real number. That's important. Is there a rule that allows me to take this and simplify it? The answer is yes. A square roots of b squared is the same as a squared times the square root of b squared. But that's the same thing as a squared times the square root of b squared. And whenever you have a square root and a power of 2, they cancel each other out, and we'll be just left with b. So the final answer is a squared times b. And so that's the rule that I used to help me reduce these numbers as quickly as possible. All right, one more mistake or myth that students fall into, and then we'll be done. Okay, let's talk about one of the last mistakes or myths that my students sometimes believe. And sometimes students believe that if it's a triangle, then it's got to have a hypotenuse. That is false. A right triangle has a hypotenuse. Other types of triangles do not. And the reason is simply because of the definition of hypotenuse. A hypotenuse is the side of the triangle that's opposite the 90 degrees. And other types of triangles that are not right triangles don't have 90-degree angles. So they can't have hypotenuses, if that's the plural. Here's a triangle. Is it a right triangle? Yes, this is a right triangle. So the Pythagorean theorem works. Can you figure out what y is on your own? I'll tell you at the end of the video, okay? You find out first. Pause the video, see if you can find it, and then I'll tell you at the end of the video what it is. Here's a triangle. ABC, I know 2 sides, and the third side, Z, I don't. Can I use the Pythagorean theorem? This is not a right triangle. So the Pythagorean theorem does not apply. It just doesn't work. And so don't fall into the misconception that every triangle has a has a hypotenuse. No, it's only the right triangles that have a hypotenuse, and only them. So the Pythagorean theorem can only work on a certain family of triangles. It can only work on the right triangles. All right, here you go. The value of y is 12. God bless you, wherever you are today.
I'm not sure. I'm afraid we need to use math.